conveniently connected to power and ground. So if you do the truth table, you'll see whatever you put at the input, the opposite will come out at the output. So it's an inverter. Every other logic gate will be similar to this. This is one with four transistors, and if you look at how they're connected to each other, you'll see that the truth table gives you a 2-NOR function. And you do that for every gate. And how long does it take to understand these, starting from scratch, Starbuck? Maybe 2 days? 2 days, yeah. So after 2 days, you should be able to read these and all the other ones. If you don't want to spend the time, just go to Silicon Zoo. We already put a nice collection of the ones we have, and we'll be uploading constantly more. So it's a good exercise to try to understand these. If you don't want to spend the time, go to Silicon Zoo and download some collections there. So we now understand how we can look at the logic gates and understand what they are. What we don't do is search all across these 10,000 or so gates and try to figure out which is which. So we wrote some MATLAB scripts, and the MATLAB scripts, they use face recognition algorithm. So we tell the MATLAB script, hey, look up here, there's a face. Where are other faces in this photography? And it will find other faces. And then we'll tell, okay, here's another type of face. Find similar faces, and it will find this again. And so just after a few clicks, we get a nice coverage of the entire chip. And it will tell us what logic function is where on the chip. Good so far? So we get a map of what logic function is where. Next step is clearly finding how they're connected to one another. A step that Starbuck again spent a lot of time on doing, especially debugging, to build a ground truth for us so we can automate this step. But conceptually, what you do is you start at some point where you know this connection has to be connected to some other gate. And you trace it across different layers until you hit some other connection. And then you know that this 2-NOR is connected to this flip-flop over here. He did this couple of thousand times total. And we now have nice ground truths to train our program, which has been written by Nitram. Nitram here anywhere? No? Nitram will be releasing software very soon, which I'm very excited about. So Nitram software is taking this image on the left and finding the different metal wires and the connection between the metal wires. So it's basically giving us this extra information, what is connected to what else. His software also does all the other things that my MATLAB scripts are doing. I was going to release all the MATLAB scripts, but his so much nicer. We'll just wait the next week or two until this is ready. I'm definitely excited about it. So we have a map of where everything is on the chip, and we know what is connected to what, which gives us a circuit plan, right? And the circuit plan is basically equivalent to source code. It's very messy source code because it wasn't ever meant to be read back, but it's nice enough for us to understand the functionality behind it. Is that clear so far? That we can find the circuit just from polishing Simple Microscope, few open source programs? Good. There are a few things that people tell us would prevent what we do, and I'm just going to go through this list to make sure it has been mentioned that this is not the case. People do a lot of obfuscation in hardware design to prevent people like Chris Stanovsky from FlyLogic from just looking at the chip and telling you immediately what is connected to what. Now, our computer programs, our MATLAB scripts, they approach this problem a little differently. They start from point A and look where's point A connected to, and they see, oh wow, there's a connection, and they don't care how it's routed. Obfuscation works something like this. If you have an 8-bit data bus, you just scramble all the lines. Now if Chris from FlyLogic goes line by line, reads it out, he reads only garbage. Now our computer script doesn't even understand the concept of intuitive wiring. It just finds what is connected to what. The same goes for dummy functionality. So in chip design, to, again, irritate reverse engineering, human reverse engineering, extra functionality is added, functionality that doesn't actually contribute to the output. Now, we start from the output and reverse engineer to wherever we expect the input to be, and we'll simply ignore the dummy functionality. Now, one feature of a chip that still does make it very difficult for us to reverse engineer is our very large chips. Mostly though because I'm a terrible programmer and Nitram's program isn't ready yet, but when somebody picks up the challenge of scaling up these ideas to whatever chip you want to work with, this will scale to a Pentium easily if you want to. And I would expect in a Pentium to be to find very interesting bugs that will allow you to circumvent things like OS abstraction, security levels. You might be able to create your own ring, these types of things, right? So I'm sure at some point somebody will pick up this challenge and there will be bugs. There has been one bug being found and published at Hack in the Box, I think. I don't know how they found it, but reverse engineering will allow you to find a lot more. And now there's this last thing. People tell us once you start messing with our chips, they blow up or something, they break. That reminds me only of the Da Vinci vial where some vinegar breaks, but anything short of some acid inside the chip to break the structures will not do what people think that the microchips are able to do. Sometimes a microchip will delete memory contents, but break a physical structure such as the ones we are reverse engineering, that is not possible. So there isn't really a countermeasure to what we're doing. That's the whole point. If you're not convinced yet that you should be doing this too, yes, a very brief wrap-up of the impact we had was when we looked at the MIFARE RFID chip. So we released this exactly a year, well, we announced that we had broken it exactly a year ago here at the Congress. And shortly after, thanks to Brenno, who immediately in the new year wrote about it, a big discussion took place, mostly in the Netherlands, but then some other countries following, about using proprietary encryption. Went all the way to the Dutch Parliament, for instance, where it was decided that this was not a good technology to use. And the whole outcome was just tremendously constructive in that an understanding was created how to deal with cryptography in public systems and what types of devices not to use. And the consensus today, I think, is to only ever use standard cryptography. So that's a nice outcome. But we're not quite there yet at secure systems. And I'll briefly give an outlook over what I think is the next huge security vulnerability in hardware systems, and then we can have some discussion on what you think, where this technology or these techniques should be taken. So I think we are pretty good on cryptographic functions. In the field, we still have a lot of proprietary technology, but everything that comes out new should be implementing AES, RSA, any of those, and devices are already available in pretty much any market. But once this chain, this link of the security chain has been fixed, the next weakest link, I think, will be key storage. So that there are many copies of master keys flowing around in these hardware systems. Not if you store them online, which you might think pretty much every system does, because you do it on the internet. You store your master key in a fortress, basically, guarded by physical security and protected by your best sysadmins. In hardware systems, that's not actually possible most of the time. Because if you swipe a card to get into a building, you need a response within a fraction of a second. And you can't just call into your data center, do some processing, and call back. So there are copies of the secret key either stored during the runtime of the device. So if the device, say the reader at your door, boots, it will copy the key from the server, often to RAM. Anybody who knows anything about cold boot attack will know that this is a terrible idea. So don't do this ever. Or the device is locked away, the key is locked away in the device in what industry calls a secret key storage or a key storage. And only a master key is locked away for the following reason. In a system with millions of users, first of all, you couldn't store a list of all the millions of keys. Well, obviously, you don't want to give the same key to every user. But then also, even if you could store it somehow compressed on your device, the list is constantly changing. So to get around all these problems, you store one master key and then derive the key for each of the users from that master key. Makes sense, right? Now, this master key has to be stored in secure hardware. And these secure key storages come in very different flavors. They come from big appliances that you'll find in banks, for instance, for the ATM network, all the way down to SIM cards. So a lot of people store secret keys on SIM cards, yes. And all of these have to rely on proprietary algorithms for the following reason. So the master key is stored in some encrypted form because you can always read out memories. And if you read out the memory of this chip that stores the master key, you don't learn the master key yet, but rather some derivative that will be different for every appliance. When the master key is needed then, it's decrypted using a decryption function that is built into the chip, but that is secret. Now we're back to proprietary encryption, which is exactly what we've been breaking all along, MIFARE and a couple of other examples. So we've just reduced the problem to one that we already know how to solve. We can get the master key by reading out the memory on these devices and by reverse engineering the proprietary encryption function that is on this device. SAM chips are none the better. In fact, these are the SIM card shaped key storages. They have much lower security yet. Oftentimes you'll find keys either plain text in the RAM, or you can wiretap what I've shown in the beginning. So really there is no good solution for secret key storage. And I don't know how to build this solution. What I'm trying to get across, though, is that if you are building hardware and you are already using good cryptography, do not rely on the fact that your keys are securely stored. Try to store them in as few places as possible and prepare for the case where your master key gets compromised. Have good key rollover schemes. So that would be one advice. If you are building hardware software, prepare for failure, roll over your keys often, be a moving target in general. Layer a lot of different security functionality and keep changing it. So if any one piece of your security puzzle fails, nothing or only a very small fraction of your population is affected. Obviously, use standard ciphers, but everybody already knows that. And that is as far as I brought material, but I'd love to have some discussion with you about hardware security and about where you see the next weaknesses. But so far, thanks for your attention.
Just a small question. The SAMs, the original MIFARE chip that you mentioned, is that on? I mean, wouldn't one way of circumventing your inspection of the chip be scaling it down to a smaller process? Is there a lower limit of what size process? For example, could you reverse engineer something really tiny like the Core Quad processors?
Mm-hmm. We couldn't reverse engineer it with the tools we have, but there's imaging technologies such as a focused ion beam that can image basically anything that can be produced. And in fact, if you could produce a microchip that nobody can image anymore, you wouldn't be able to debug it. So it's crucial for the process of making a microchip to be able to reverse engineer at least parts of it. Every microchip fab will have a reverse engineering lab built into it. We don't have a FIP, but we have access to one, so we can break pretty much